This lesson is over graphing rational functions. A rational function is formed by the quotient of two polynomials, p of x, divided by q of x, where q of x, the denominator, cannot equal 0. An example of a rational function would be f of x equals 1 over x minus 3. Now recall, whenever we have rational functions or fractions, the denominator cannot equal 0. So, in this case, our denominator happens to be x minus 3. So x minus 3 cannot equal 0, and if we solve for x, we find out x cannot equal 3. Well, that affects our domain. So if 3 is removed from our domain, then what is left? Well, that means our domain would be from negative infinity to 3, close parenthesis, union, picks back up at 3 with the parenthesis, and continues to the right to infinity. Now, we know x cannot equal 3, but what happens as we approach 3? Well, let's look. Still looking at the function f of x equals 1 all over x minus 3. Let's see what happens before 3. So in a t-chart, I'm going to choose some values. Before 3, you may think of the number 2. Now, are there numbers between 2 and 3 on the number line? Yes. So let's look at a few of those values. How about 2.5? Maybe even get a little closer. How about 2.9? And maybe even closer than that. Maybe 2.99. Now, all of these values are approaching 3 from the left side. Now, if you think of the number line, the furthest left is negative infinity. So negative infinity approaching its way to 3 from the left. Now, those are all the values before 3. Let's look at some values after 3. So we make a separate t-chart. The most common value after 3 is probably a 4. But are there any values between 3 and 4? Yes. So let's look at 3.5. Maybe get a little bit closer. 3.1. And even closer. 3.01. So these values approach 3 from the right. And if you think of the number line, the furthest to the right is positive infinity. So we've got these two t-charts. Now I want you to take a moment to plug these values into the function and find the corresponding result. Hopefully for the values before 3, you found 2, negative 1, 2.5, negative 2, 2.9, negative 10, and 2.99, negative 100. Now let's see how you did for the values after 3. Hopefully you found 4, 1, 3.5, 2, 3.1, 10, and 3.01, 100. So since we have these t-charts, we are going to graph them. The majority of the points are realistic. We are not going to include the points that go all the way up to 100 or a negative 100, but the other ones are reasonable. Take a moment now to plot the other points. For the values before 3, your graph should look similar to mine. For your points after 3, your graph should look similar to mine. Now notice, we have none of the values actually at 3. But what happens is we actually have this imaginary brick wall or this force field that's taking place. This break is what's called a vertical asymptote. Let's talk more about that. Determining vertical asymptotes. For a rational function, f of x equals p of x over q of x, where p of x and q of x are polynomials with no common factors other than constants. If a is a zero of the denominator, then the vertical asymptote will be of the form x equals a. An important piece is that the function f of x needs to be in reduced form. Example 1, determine the vertical asymptote. For a, we have f of x equals, and in the numerator we have 2x minus 11. In the denominator we have x squared plus 2x minus 8. Now, to determine vertical asymptotes, it says where the polynomials have no common factors other than constants. Well, the only way to identify if they even have common factors is if they're written in factored form. So we look at the numerator, 2x minus 11. Can that factor? No, because it's linear and there is no common factor. So now we look at the denominator. Can that factor? Yes, that is a quadratic, so take a moment now to factor the denominator. The denominator does factor into x plus 4 and x minus 2. So now that both the numerator and denominator are in factored form, we look to see if it has any common factors. If possible, we reduce. But in this case, there is no common factors, so we continue on with the definition. It says if a is a zero of the denominator, then the vertical asymptote will be of the form x equals a. Well, in the denominator, we have two separate pieces. We have an x plus 4 and we have an x minus 2. So we take the first piece and we set it equal to 0. So x plus 4 equals 0. And the other piece, x minus 2, set equal to 0. From here, we solve the two equations, and this will be our vertical asymptotes. Solving for x in the first case, we would find x equals negative 4. And in the second case, we would have x equals 2. These are your vertical asymptotes. So visually, it means you would have these two vertical imaginary force fields that are affecting the graph. Let's look at another example. Example B, f of x equals x squared minus 4x in the numerator, and in the denominator we have x cubed minus x. Now we're trying to identify vertical asymptotes, and we can only do that if it's in a factored form. So we need to factor. Take a moment now to factor the numerator and denominator completely if possible. In the numerator, you should have found there was a common factor of x, which left you with x minus 4. In the denominator, you should have also noticed it had a common factor of x, which left you with x squared minus 1. But notice x squared minus 1 is the pattern of difference of squares, so it does factor again. So it does factor the denominator into x times x minus 1 times x plus 1. So now that we have the factored form, we need to, if possible, reduce this. Is there anything that appears in the numerator and in the denominator? Yes, we have a common factor of x, so we must reduce the x, which leaves us with the function x minus 4 all over x plus 1 times x minus 1. Now in the reduced form, the vertical asymptote is any values that cause the denominator to equal 0. In the denominator, we have two factors, so we must set them each equal to 0. The results will give you the vertical asymptote. So x plus 1 equals 0 would tell you x equals negative 1. The other factor of x minus 1 equals 0. When you solve for x, we'll find x equals 1. So your vertical asymptotes are x equals negative 1 and x equals positive 1. Again, visually, this means we have two vertical force fields that are happening that are changing the shape of the graph. Now, in this case, we had a common factor. What about that? Let's see. Determining holes in a graph. The hole is an open point on the graph. The hole is determined by the common factor. Now we know the x-coordinate of the hole by setting the common factor equal to 0 and solving. But to find the corresponding y value, we must plug the x value into the simplified form of the function. Example 2. Determine the domain, holes, and any vertical asymptotes. For A, we have the function f of x equals. In the numerator, we have x minus 2. In the denominator, we have x squared minus x minus 2. Now, this is written in what's known as the expanded form. Expanded form simply means you see the highest degree. Everything's already multiplied out, nothing is in factored form. Now, although expanded form is a helpful form, it does not help us identify the domain, any holes, or vertical asymptotes. So from here, what we need to do is we need to factor. So take a moment now to factor the numerator and the denominator if possible. Hopefully you found the function f of x to equal x minus 2 all over, and in the denominator have x plus 1 and an x minus 2. Again, this is known as the factored form. Now the factored form is very helpful. It helps you first identify the domain. Now we know when it comes to domain, there's two key issues that cause problems: fractions and radicals. Well, our particular problem is a fraction, and we are concerned with the denominator. In the denominator, in the bottom, we have two factors that could potentially be equal to 0. And the numbers that would cause those to equal 0 would be negative 1 and 2. So to properly write the domain, I'm going to draw the number line. And the two values that cause problems have to be written on the number line in the correct order. So negative 1 would appear first, then the value of 2. We know that x cannot equal negative 1 or 2, so we place open circles on the number line. Now from here, x can be any of the values to the left of negative 1, in between negative 1 and 2, and to the right of 2. So now that we see the number line, we can now write our interval notation. Our interval notation would go negative infinity to negative 1, union, negative 1 to 2, union, to infinity. So that helps us identify our domain. Now, from the factored form, what else can we identify? Well, any possible holes. How do we find holes? Well, holes are identified by any common factors. So we look in our factored form. Do you see any common factors? Yes. X minus 2 appears in the numerator and the denominator, which means we are going to have a hole. Now, a hole is an open point. So it is an ordered pair that consists of an x value and a y value. It says we know the x coordinate by setting the common factor equal to 0 and solving. Well, x minus 2 is the common factor. If we set that equal to 0 and solve, we find x equals 2. But from here, we cannot find the corresponding y value yet. It says you can find the y value from the reduced form. In other words, once you've removed the common factor. So once we remove the x minus 2's, that leaves us with f of x equals 1 all over x plus 1. This is now our reduced form. Since we have the reduced form, I can now find my corresponding y value. It says to plug in the x value, which we found to be 2, into the reduced form. So f of 2 equals 1 all over 2 plus 1. When I simplify and evaluate the fraction, I find the result to be 1/3, which means the whole will appear at 2, 1/3. Now we've identified the domain and any holes, but we still have to find any vertical asymptotes. Well, vertical asymptotes can only be found from the reduced form, which we do have. And so we look at the denominator, and what value would cause the denominator to equal 0? Well, that would be -1. So our vertical asymptote is of the form x equals -1. Example B, f of x equals -2x squared minus x plus 15 all over x squared minus x minus 12. Now this is written in the expanded form, which means I can clearly see my highest degree in the numerator and the highest degree in the denominator. But there's something you may notice about the numerator. In this case, our leading term starts with a negative. Generally, we don't like it to be a negative, so our first thing is we are going to factor out a negative or a -1. When you factor out a negative from the numerator, it changes all the signs. So in the numerator, I now have negative, parentheses, 2x squared plus x minus 15, close parentheses, still all over the same denominator. Now, we're trying to identify the domain, which means everything has to be in factored form. Well, in the numerator, I still have a quadratic in the parentheses, and I still have a quadratic in the denominator, so they both need to be factored. Take a moment now to factor the numerator and the denominator. In the numerator, remember we still have the negative that we factored out first, and then you should have a factor of 2x minus 5 and an x plus 3. In the denominator, it should factor into an x minus 4 and an x plus 3. So now we have the factored form. From the factored form, we can now identify the domain. Now, to help us write the domain, we are going to draw a number line, and we're concerned with any values that cause the denominator to equal 0. In this case, we see a 4 and a -3 would be problematic. So -3 is on the number line, and so is a +4. X cannot be these values, so they are removed from the domain, which means on the number line, they will be open circles. But I can use any values to the left of -3, in between -3 and 4, and to the right of 4. So now that I see my number line, I'm now ready to write my interval notation. It will go from -infinity to -3, close parentheses, union, parentheses, -3 to 4, close parentheses, union, parentheses, 4 to infinity. Now also from the factored form, we can identify if we have any holes. Holes are identified by any common factors. Notice we do have a common factor of x plus 3 appearing in the numerator and denominator, so we will have a hole of the form of an open point. The x value is found by setting the common factor equal to 0, which in this case tells us x will equal -3. We cannot find the corresponding y value until we have the function reduced. So we remove the common factors and we're left with -2x plus 5 all over x minus 4. In the numerator, I simply distributed the negative sign. Now to find the corresponding y value, we plug in a -3 into the function, so take a moment now to do that. Hopefully you found the corresponding value to be 11 over -7. Now that we've identified the whole, we're ready to identify any vertical asymptotes. Vertical asymptotes will be found by setting the denominator equal to 0. And when we do that, we will find x equals 4.